Hello and welcome everyone to our weekly session titled Latest in Bitcoin Tech, where we go through the Bitcoin Optech newsletter. And this week we will go through newsletter number 322, published 3 days ago on September 27th, 2024. This week's newsletter contains a news section and a monthly feature, which is selected questions and answers from Bitcoin Stack Exchange, releases and release candidates, a notable code and documentation changes. So we have four news articles. Let's see how many we can cover. At least let's try and cover two of them, and then we can move on to the Bitcoin Stack Exchange Q&A section. All right, so we'll go through the preface of the newsletter. This week's newsletter announces a fixed vulnerability affecting all versions of Bitcoin code, provides an update on hybrid channel jamming mitigation, summarizes a paper about more efficient and private client-side validation, and announces a proposal to update the BIP process. Also included are our regular sections summarizing top questions and answers from the Bitcoin Stack Exchange, announcing new releases and release candidates, and describing notable changes to popular Bitcoin infrastructure. So the first news article is about Bitcoin Core, and this is in sequence to the list of vulnerabilities that do not affect latest versions of Bitcoin Core. So we have talked about this in preceding sessions about an update in the protocol of announcing or responsibly disclosing Bitcoin Core of vulnerabilities, and how a lot of vulnerabilities that do not impact versions of Bitcoin Core that are being maintained right now were released in the preceding newsletters, and this is a continuation of that. Another vulnerability that does not impact any versions of Bitcoin Core that are actively maintained has been released. So this version, which is 24.0.1, has reached end of life, and this vulnerability does not impact any Bitcoin Core client version after 24.0.1. So let us see what it is. We will first read through it and then try and dive deep into it. The title is Disclosure of Vulnerability Affecting Bitcoin Core Versions Before 24.0.1. Anton Ponsop posted to the Bitcoin Dev mailing list a link to the announcement of a vulnerability affecting versions of Bitcoin Core that have been past their end of life since at least December 2023. This follows previous disclosures of all the vulnerabilities. So they are referencing the previous vulnerabilities that they had disclosed in newsletter 310 and 314, both of which we have covered. The new disclosure discusses a long-known method for crashing Bitcoin Core full nodes, sending them long chains of block headers that will be stored in memory. Each block header is 80 bytes, and if there were no protections, could be created at the protocol minimum difficulty, allowing an attacker with modern ASIC mining to produce millions per second. Bitcoin Core has had protection for many years as a side effect of the checkpoints added in an early version. These prevented an attacker from being able to create the initial blocks in a chain of headers at minimum difficulty, forcing them to perform significant proof of work that they could instead be paid for if they created valid blocks. So primarily, this vulnerability has to do with a denial of service attack. Basically, your node could be overwhelmed in a manner that excessive data is supplied to it to store and process within a very short amount of time, which is beyond its computational power and beyond its resources, leading to a crash in your Bitcoin node. Now, how does this happen? Briefly, as an overview, before we go into more detail, when you spin up a Bitcoin node from scratch, okay, when you bootstrap a node, your node has no prior information about the blockchain except the genesis block, which is hard-coded into it. So it establishes connections with peers, and these peers feed or gossip relevant information pertaining the blockchain, which the Bitcoin node uses in order to sync the information that is needed for it to be on par with the current active chain tip. It starts from the second block after the genesis block and keeps syncing and validating each transaction and validating each block till it syncs with the active chain type, the current chain type. Okay. How does a Bitcoin core node validate that it is syncing with the right chain, right? It's absolutely possible that when a node syncs up from scratch, it establishes connections with malicious peers, right? It can establish connection with malicious peers that might gossip wrong or erroneous data to it. So there needs to be a mechanism to check whether the information that your node is processing, receiving, the information that your node is relying upon in order to sync with the blockchain is appropriate information. And that is why there need to be checks in place to ensure that the Bitcoin core node that is syncing with the correct blockchain. Now, one mechanism of doing that is known as checkpoints. So earlier, what used to happen is that whenever Bitcoin cores, or back when it was even known as Satoshi's implementation, which is now known as Bitcoin Core, uh, when Bitcoin Core would be released, like major versions of Bitcoin Core would be released, periodically checkpoints would be inserted or hard coded into uh, the software, all right? And they were header hashes of blocks at certain intervals. So when your node was syncing and it came across a certain block, it would validate or verify whether the header hash that the peer has sent it corresponds with the header hash that has been hard coded in the client. And if it does, then it means that it is syncing with the appropriate blockchain. So, right, so just like we have checkpoints on roads, on pathways, right? So if you're moving from direction A to direction B, there are generally checkpoints which assure you that you're moving in the right direction. So if you're going from place A to place B and if you see that place B is 100 kilometers away, and then you drive for 15 minutes and then you see that place B is now 90 kilometers away, and then you drive for 1 more hour and then you see that place B is now 50 kilometers away, it ensures you that you're moving in the right direction and eventually you will reach your destination, that being place B. So similarly, hard-coded checkpoints were incorporated into Bitcoin Core that ensured the nodes, while they were syncing up with the blockchain, that they are syncing up with the correct blockchain. They've gone through those checkpoints in the preceding sessions, but because I have my VS Code open, I was going through it some time ago, so I think we can have a look at it again for those of you who did not attend that session. So these are checkpoints, and I am in chainparams.cpp. So these are the checkpoints that were embedded. This is the block height. Okay, so this is the block height, and this is the header hash. This is the header hash. So when your Bitcoin node is syncing and its peers are giving it information, right? And when it reaches this block height, it will validate that the hash of the header that the peer has shared with it corresponding to this height is the same hash header or no. If it's the same hash header, it ascertains that the node is syncing up with the correct blockchain. If the peer of the node shares hash header which has the same block index but does not have shares a block which has the same uh, block index as this but does not have the corresponding header hash, or shares a header hash which is this but does not correspond to the same block index, it means that the peer is sending it erroneous information, right? And that is a red flag that we need not rely on, or we cannot in fact rely on the information that is being shared by this peer. It's a malicious peer and we should evict that peer from our address list. And then periodically those checkpoints were increased, right? So again, there's a second checkpoint at this block height, there's a third checkpoint at this block height, there's a fourth, fifth, sixth, and the final checkpoint that we have is at this block height, okay, 295,000. And this was, I believe, in 2014. So the last checkpoint that was incorporated in Bitcoin Core was 2014, after which checkpoints were not introduced anymore, after which a different mechanism was used to validate or verify whether you are syncing with the right blockchain or not. Would somebody like to take a shot at why were checkpoints abandoned? And by abandoned, I mean why were checkpoints not updated after 2014, after this block height? What was the reason for checkpoints not being incremented? Like what loophole can you see in this mechanism? Why can't we why are checkpoints not the best way to determine whether you are in sync with the right blockchain or not? Would anybody like to take a shot at that? Is anybody typing something? No. All right, fine. So basically, what happens is if the peer is sending you malicious data, uh, before reaching a checkpoint, you have no way to determine whether the node is cheating you, the peer is cheating you, right? So you, until and unless you do not reach this height, there is no way for you to ascertain that correct information is being shared with you. You already have the genesis block incorporated into the client software. After that, the first checkpoint you have is this block index height. So from the genesis block up till this height, there was no way for you to ascertain that the peer is sharing correct information with you. All right. So it was possible for somebody to eclipse attack you and share malicious information, wrong information, and only after you reach this checkpoint was it possible for you to validate whether that information was correct or no. Okay. So ideally, we don't want that scenario. We don't want to download so many blocks and then after that get to know that we've been cheated. We want to know from the admin, from the word go, from the onset. We need to know if somebody is cheating us, and if they are, then we should not trust them. So that is why checkpoints were done away with. What do we do now? We use another mechanism. We use another mechanism while syncing up to the blockchain to verify whether the information that the peer is sharing with us is relevant or no, it's appropriate or not. Okay, so I'll just read this once again. The new disclosure discusses a long known method for crashing Bitcoin full nodes, sending them long chains of block headers that will be stored in memory. Each block header is 80 bytes, and there were no protections, and if there were no protections, could be created at the protocol minimum difficulty, allowing an attacker with modern ASIC mining to produce millions per second. Bitcoin Core has had protection for many years as a side effect of the checkpoints. We just discussed what checkpoints are. So until 2014, checkpoints were installed at regular intervals. Post 2014, a more robust mechanism was deployed. These prevented an attacker from being able to create the initial blocks in a chain of headers at minimum difficulty, forcing them to perform significant proof of work that they could instead be paid for if they created valid blocks. However, the last checkpoint was added 10 years ago, and Bitcoin Core developers have been reluctant to add new checkpoints, as doing so gives the mistaken impression that transaction finality is ultimately dependent on developers creating checkpoints. As mining equipment has improved and the amount of network hash rate increased, the cost to create a fake chain of headers has decreased. As the cost decreased, researchers David Jansen and Braden Fuller independently responsibly disclosed the attack to a Bitcoin Core developers. Developers replied that this issue was known to them and encouraged Fuller to publicly post his paper in about 2019. Is this the paper that mentions it? Right. Okay. So this diagram just manifests how it's possible for someone to create a fake chain, a chain of fake headers, right? So you have checkpoints till 2014. After 2014, you do not have checkpoints. So an attacker, what they can do is after the last checkpoint, they can fork off. They can fork off and start mining on a parallel chain by reducing the difficulty. Now, because they're mining on a parallel chain, nobody else is competing with them, right? On this chain, on the honest chain, there are a lot of miners competing with them. And that is why the difficulty of this chain is very high. But if you fork away and you're the only miner mining this blockchain, then the difficulty is very low, right? So it's possible for you to create low difficulty blocks. It's possible for you to create low difficulty blocks and then share that dishonest low proof of work chain. Share that dishonest low proof of work chain over here, right? So the cost of creating a dishonest low proof of work chain is very little if we rely only on checkpoints. All right. In 2022, the cost of the attack having decreased further, a group of developers began working on a solution that did not use checkpoints. Bitcoin Core PR 25717 C newsletter 216 was the result of the work. Later, Nicholas Gerber discovered a bug in 25717's logic and opened PR number 26355 to fix it. Both PRs were merged and Bitcoin Core 24.0.1 was released. Okay. So what is the new mechanism that we use? Let us see. I think it's mentioned in this PR, right? So until 2014, we were using checkpoints. So when the node was syncing up, when it was receiving information from the peers, it would validate whether that information which is being shared by the peers is accurate or not by referring to the checkpoints. It would come to the checkpoint and validate the block index against the header hash. And if both correspond to the value that is hard coded in the client, then it would ascertain that the node is syncing with the correct blockchain. Otherwise, the node would be intimidated that it's syncing with the wrong blockchain. Okay, but and what was the drawback in it? We discussed the drawback as well. Until and unless you reach a checkpoint, it is not possible for you to validate whether you are being fed right information or not. Okay, so that mechanism was replaced by a more superior mechanism. What was that? That was this PR. What does this PR do? It adds a header presync step during initial block download to help prevent denial of service attacks and step towards removing checkpoints. Nodes use the presync phase to verify that a peer's header chain has sufficient work before storing them permanently. Okay, so just now we saw in this paper how it's possible for an attacker to fork off the chain and start mining blocks at very low difficulty and keep on decreasing that difficulty with every passing uh, difficulty adjustment period. So after every 2016 blocks, the difficulty can be reduced further by 1/4, and then again by 1/4, and then again by 1/4 till the difficulty reaches the minimum difficulty of the network. And at minimum difficulty of the network with modern ASICs, it's possible to create hundreds and thousands of blocks within a second. I think even millions of blocks in a second. It's possible at minimum network difficulty. And then that attacker can feed that chain to a peer that is trying to sync up, and with that they can overwhelm it with exhaustive data processing, and storing that information would not be possible for the node. The node would get overwhelmed and get crashed, or the node will crash. That's a DOS attack. That's a denial of service attack. Okay, so how do we prevent that? We prevent that by, as discussed, by a headers presync. A headers presync. What do we do now? Now every single block that a peer receives while it is syncing up to the blockchain, it validates whether that block has adequate amount of work or not. So it first processes only the header. It first processes only the header of the block, and it ensures that the header of the block refers to adequate amount of work. Only if the block has adequate amount of work, that specific block has adequate amount of work, will that block be considered valid. And then the cumulative work of all the headers up till that point in chain will also be validated. And if that reaches the threshold, that reaches the amount of work that is required for a chain to be valid, then the block will be processed. So for instance, I'm syncing, and I've completed the sync up till block 100. Okay, so now I will ask for the header, only the header of block 101. I will check if that specific block, only block number 101, has adequate proof of work or no. If it has adequate proof of work, then the first check is passed. The second check is that whether after adding that block 101 to the 100 blocks that I already have, the cumulative chain of 101 blocks, does that cumulative chain do all the blocks put together have adequate amount of proof of work that is required for a chain to be valid? And if the answer is yes, then that block will be processed. Okay, so initially we used to only download the headers first during the pre-sync. Now we do two things. First, we ask for the header and validate whether they have a proof of work. We don't store them in the memory. We ask for the block and validate whether that we ask for the header and validate whether that header has adequate proof of work. If it has adequate proof of work, then we download it. All right, that is the change that's been done now. What does it do? Adds a headers presync step during initial block download to help prevent denial of service attacks, and step towards removing checkpoints. Nodes use the presync phase to verify that a peer's headers chain has sufficient work before storing them permanently. During IBD, adversarial peers may attempt to stall the syncing process, serve blocks that don't lead to the most work chain, or simply exhaust the node's resources. As such, while sync speed and bandwidth usage are important concerns during IBD, our primary design goal is avoiding denial of service attacks. Since version 0.10.0, Bitcoin Core nodes sync block headers first before downloading block data and reject headers that don't connect to a set of checkpoints. Instead of using hard-coded values, this new design utilizes the inherent toss-resistant property of proof of work puzzles to minimize the amount of memory allocated before finding the main chain. So initially, what used to be done is that we used to ask for the headers. Okay, we used to ask for the headers and store those headers in the memory, and then validate those headers with the hard-coded value of the checkpoints. Okay, now we don't do that. We do that, but before that, what we do is we ask for the headers and verify whether the header has adequate proof of work before storing it into the memory. Only if the header has adequate proof of work do we then download that header and store it in memory. Okay, so now we do two rounds. With these changes, nodes download headers twice during initial header sync. A first pass to verify the headers proof of work without storing them. So first time you ask for the headers, okay, and verify whether that header has adequate proof of work without storing them until the accumulated work meets a predetermined threshold. And then a second pass to store them to prevent an attacker sending the main chain during pre-sync and then a different malicious chain during re-download. The node stores commitment to the headers chain during pre-sync. So what an attacker can do is that, like just now I mentioned, there are two rounds. In round one, we validate whether the headers have adequate proof of work, and in round two, we download the headers. What an attacker could do is that it could send an honest header during the validation phase and then send a dishonest or a corrupted header or an invalid header during the downloading phase. Okay. So to combat this, to mitigate this risk, what do? We store the commitments. We store the commitments to the header chain during pre-sync. So we store the commitments of the headers when we validate their proof of work, and when we actually download the header, we validate the downloaded header against the header whose proof of work we had validated earlier. And if both of them are the same headers, then we proceed. So this is a change that has been brought about by this PR 25717. What do we have? Do we have anything to read in this post that we've not already covered? Public disclosure. Yeah, let's just read this. So I will zoom it a little. Bitcoin Core stores the blockchain headers in memory. This makes it susceptible to being lost by having it download and store extremely long chains of headers, even if they are of low difficulty. It is important to note that once crafted, an attack chain could be reused to crash any node on the network. The possibility of using this to attack nodes has long been known and was the primary reason why the checkpoint system was still in place. Making an attacker start an attack at the last checkpoint makes it far more costly than starting at the genesis block. However, over time, with decreasing hash rate costs, even then, this mitigation becomes less effective. Okay, so earlier with the kind of hash rate we had, with the kind of ASICs we had, with the kind of computation power we had, it was relatively expensive for a miner to fork off the last checkpoint and then create a chain of fake headers. But with the advent of modern day ASICs, it is absolutely possible. It is a low cost attack. It becomes a low cost attack for a miner to fork off the last checkpoint and mine separately on a parallel chain and reduce the network difficulty till he brings it down to the minimum network difficulty, as is stated over here. This attack was independently discovered and reported to the Bitcoin Core project in January 2019 by David Jameson, who suggested introducing newer checkpoints as a practical mitigation. This still leaves the nodes performing IBD with no protection before they receive checkpoint blocks. Okay, so if you only rely on checkpoints, then before you reach the first checkpoint, it's actually possible for somebody to fake you, send you invalid headers because
I think there's some voice disturbance at your end, or at least I can feel that. What do others find it okay?
I think the pattern that I'm observing is that every 5 to 10 minutes there is some disturbance, but then it goes away after a few seconds, maybe 20 seconds or about that time.
Okay, so because if there would have been any issue with any of the devices that I'm using, then it would have been perpetual. Like if it's happening once in 20 minutes, then probably it has something to do with the network or something because I'm using the same laptop, the same earpieces, everything is the same.
Yeah, for example, now your voice is coming perfectly, but sometimes maybe in 5 to 10 minutes or 20 minutes, it's not too much, but just for a few seconds, it has some disturbance. But then it corrects itself.
It probably has to do something with network. If you lose my voice for a long period of time, notify me. But if it's happening for 5-10 seconds in 15-20 minutes, then probably has something to do with the network. I'm assuming.
Yep.
Okay, all right, I'll continue. So it relies on the ecosystem semi-regularly adopting updated software with new checkpoints. This is another gotcha. Because what if you don't upgrade? Okay, if you constantly rely on checkpoints, what if you don't upgrade to the latest version? What if I want to use a version that is 3-year old, 4-year old, for whatever reason, I don't want to upgrade? You can't force people to upgrade, right? If somebody wants to use an older client, it's their prerogative. There might be trade-offs, but it's their prerogative. So what if somebody's using an older client? What do you do then? They have older checkpoints, right? They don't have latest checkpoints. So that is another issue that comes up when you are merely relying on checkpoints. It later got increased attention when Braden Fuller posted his chain with expansion write-up to the Bitcoin Dev mailing list in October 2019. He had previously responsibly reported it to the Bitcoin Core security list. The suggested approach was not adopted in Bitcoin Core due to concerns about network convergence when limiting the number of parallel chains. At the time, the computational cost of creating a huge low difficulty headers chain was equal to about 32.28% of a mining one block at the tip. That is a cost of about 4.12 BTC, since the block reward then was about 12.77 BTC. So in 2019, I'm interpreting this text as meaning that in 2019, when this vulnerability was brought into attention, the cost of pulling off this specific attack, was 4.12 BTC. By February 2022, the cost of the attack had dropped further to around 14.73% of the cost of mining a block. And this prompted investigation of alternative solutions. If unaddressed, the cost today, September 2024, would just be 4.4% of a block. Or what is that? That's like 3.125. That's very little. Okay, yeah, these figures translate to a cost of about 1.07 BTC. And about, this is the current, this will be the current cost. So if had we only relied on checkpoints and the last checkpoint was in 2014, then it would have been possible for somebody to create a fake chain and deceive the nodes that are syncing with merely this much amount of money. But we have a protection, and we discussed what that protection is. That is, we do not rely only on checkpoints anymore. We validate the proof of work on the header and the cumulative chain. A protection against the stock DOS was implemented in Bitcoin Core PR25717, whereby the node will first verify a presented chain has enough work before committing to store it. Let us look into this PR. We can find something alarming that interests us. Let's quickly read through it. New nodes starting up for the first time lack protection against dots from low difficulty headers, while checkpoints serve as our protection against headers that fork from the main chain below the known checkpointed values. This protection only applies to nodes that have been able to download the honest chain to the checkpointed heights. We can protect all nodes from DOS from a low difficulty headers by adopting a different strategy. Before we commit to storing a header in permanent storage, first verify that the header is part of a chain that has sufficiently high work, either n minimum chain work or something comparable to our tip. So this is how we validate the proof of work. I think I have it here. So these are the checkpoints. I think we went through the checkpoints. Let us see if we can see something more. See, this is the minimum chain work. Okay, so when you get a block, you validate that the block is coming from a chain that has minimum this amount of work. And I believe this is the hard-coded value that gets upgraded or updated with every new major release of Bitcoin Core. Okay, so if a peer shares a header with you, you validate that that header is coming from a chain that has minimum this much amount of work. And I think there are also checks performed to validate for individual blocks or individual headers? Or do we have that in validation? Yeah. Uh, So yeah, this is where different checks are performed. Like you can see, one of them has valid proof of work. So here you take all the headers, okay, and you iterate over all the headers, and you check whether that specific header has adequate proof of work or no. So proof of work is determined on difficulties, which is n bits. So n bits in the header of a block determines the difficulty. So use n bits of that specific header, and you check whether each header that is being shared with you has adequate proof of work or no. And then there are other checks that are performed as well, whether the block is mutated or no, meaning whether it has a duplicate transaction ID or no. Then you calculate headers work. Here you check I believe here you check the work of all the cumulative headers that have been shared with you. So now these are the checks that you make. So the summary is that initially we were relying on checkpoints, but that had few loopholes. So we don't solely rely on checkpoints now. Now we ask for individual headers and we validate the proof of work in the headers, and only if they have adequate proof of work, if they're coming from a chain that has adequate proof of work and the header itself has adequate proof of work, do we then download those headers. So this was done in PR 25717. Okay. And this PR got merged. When did it get merged? It got merged in 2022. This PR got merged in 2022. Okay. Now, even after merging this PR, there was some discrepancy. Uh, uh, a way to bypass this check, okay, which was further mitigated by another PR, which I did not get the time to go through. And that second PR, I believe is mentioned here. Yeah, 26355. So basically 25717 did fix it, okay, but there was some loophole in it which was also fixed in this PR 26355. So you can go through it. I didn't get the time to go through this PR. I opened it, but it was taking quite some time and I had bandwidth issues, so you can go through it. Okay. But the point being, the logic remains the same. The logic remains of PR 25717, but there was a loophole that was being bypassed and the desired result was not getting obtained. So there was some more changes made and the other PR was more. It's a very small PR, you can go through it, which fixes it. And now when a node bootstraps, then it validates the proof of work and does not rely only on the checkpoints. So this is the vulnerability that we had to discuss. Any questions about this before we move on to the next topic? Give me 1 minute.
Just one quick attempt at summarizing it. So, is it fair to say that before 2014 or before this release, only we used to use the checkpoints as the validation mechanism for verifying that that no malicious node is giving us information, and now the mechanism is to verify the header hash for whatever block the peer is sharing. Is that is that the correct summary? Is that the mechanism that we're using? Every peer that sends us blocks, we independently verify the header hash and see if it's corresponding to the valid header hash.
Yeah,
Okay.
you summarized
Thank you.
it properly.
Okay.
We were relying on checkpoints. The reason being, the cost of performing that attack was very expensive. The cost of forking off and mining a fake chain of headers and feeding it to your peer was very expensive. But since the mining hardware got upgraded and then the cost of attack kept on decreasing exponentially, there was a need for another mechanism to ensure that this vulnerability is not exploited. So 2022 onwards, when this PR got merged, we started relying on proof of work.
Yeah, Faisal, one curiosity I had. Whenever verifying the proof of work of the headers that we are getting from our peers, do we do by like block by block, or like do we get like some block of headers and then we verify like in a group we get the headers and then we verify whether
No,
the
each header. You see, you are iterating over each header here. Okay, so you have all the headers, okay, and then you start iterating. You take the first header, that is when you begin the iteration. and this is C, and here is where you end the iteration. So this is the area over which you iterate, the first header and the last header. And here you can see here we have plural headers. Here we have header. We have a single header. So we validate the proof of work in each header. The moment we find a single header that is not valid, we reject that header.
Okay, okay. And in the blog, it was mentioned we do this process 2 times. Once we get the headers to check the proof, the POW is correct or not, and then we again ask. Then we this the node keeps all the header in their memory, and then they ask for header to the peer, and then they checks if the second time whatever the header that we got, whether it was matching with the header that they have sent for the first time.
Right. So first time we do download it. First time we just ask for the header. We validate the proof of work. If the proof of work is valid, then we store a commitment to that header. That commitment I believe is the hash. We store the header hash, only the header hash. Okay. Then second time we again ask for the same header and we download that header, and we validate and we check the header of the downloaded, and we check the hash of the downloaded header with the hash that we already have. And if it matches, then it's a valid header.
Yeah, got it. So only second time if the check got passed, only in the second run we download the complete blockchain, and we at that time we check the header of the particular block with the header that we have previously received.
Right, because in round one we don't even know whether this header is valid or no. So there's no point storing it or keeping it in memory. We are still unaware whether that header is a valid header or not a valid header. In the second round, we have already verified that the header is a valid header. Then we can ask for the header and just download that header. Just validate its commitment and then download that header.
Yeah, yeah, got it, got it.
Okay, all right. Let's move on to the next one. We'll try and do this a little quickly because we have Stack Exchange questions and answers as well. We have about 15, 25 minutes. And in 10, let's try and wind this up. So let's try and finish this in 10 minutes. This shouldn't take a lot of time. We'll not go into a lot of detail. So hybrid jamming. So jamming is a kind of attack that is performed on the Lightning Network. This news article has to do with the Lightning Network, and jamming, as the name suggests, it jams the network. Carla Cohen posted to Delving Bitcoin details about various attempts to defeat an implementation of the mitigation for channel jamming attacks, originally posted by Clara Schickelman and Sergey Tikhomirov. Hybrid jamming mitigation involves a combination of HTLC endorsement and a small upfront fee that is paid unconditionally whether a payment succeeds or fails. Several developers were invited to attempt to jam a channel for an hour, with Kirk Cohen and Schickelman expanding on any attacks that seemed promising. Most of the attacks were failures. Either the attacker spent more to use the attack than another known attack, or the target node earned more in income during the attack than it would have earned through a normal forwarding traffic on the simulated network. So basically, this news article permeates from an event where Lightning developers were invited to perform a jamming attack. On the Lightning Network, and this is done pretty often. That developers are invited to stress test or to attack a protocol or a tool, so that the vulnerabilities in it can be made known. Okay, so what was the task? The task for that was that several developers were invited to attempt to jam a channel for an hour. To jam a Lightning channel for an hour, that was the task given to the developers. One attack was successful. Okay, it was called a sync attack that aims to decrease the reputation of a target's node. Okay, so now let us directly go into the post because we don't have a lot of time. So let's look into the post. I think this is going to be helpful. Right, I think so. What is a channel jamming attack? What is channel jamming? A channel jamming attack is a long known denial of service attack against the Lightning Network's scarce resources that disrupt the network's ability to forward payments. So, what are these scarce resources? Scarce resources here are liquidity, because liquidity obviously in a lightning channel is finite. If the liquidity is exhausted, then the channel cannot route payments anymore. And the second scarce resource is obviously bandwidth. There is only amount of data that a lightning channel can process, and if that bandwidth is exhausted, then the lightning channel cannot process any more data. This attack is executed by continuously routing payments through a targeted channel and intentionally failing the payment back so that all of the channel's resources are consumed. There are two ways in which the resources of a channel can be exhausted. Liquidity jamming. Large payments are sent to consume all of the liquidity available in the channel, right? So if you want to target a node, all right, you route large payments through that node. You route large payments through that node so that the liquidity of that node gets exhausted and it doesn't have any more liquidity to route payments. Slot jamming. Small payments are sent to hit the protocol defined limit on the number of HTLCs that a channel can hold. A channel can hold 483 HTLCs, so you route small payments to clog all 483 slots so that the channel cannot process any more HTLCs. Okay, so now what's the catch here, right? What's the catch here? How do you harm the node, right? Even if you're routing a large amount of payment, okay, if you're routing a large amount of payment, you're also paying a large amount of fee, right? You are also paying a large amount of fee, so the node is benefiting eventually. And even if you're clogging up all 483 slots, right, for every single payment that you make out of those 483, the node is getting fee, right? So what's the problem? The problem is that these payments are designed in a manner so that they intentionally fail. So you will route large amount of payments through a node to exhaust all of its liquidity, and eventually you will make sure that that payment fails. That payment fails, all right? So what happens when the payment fails? You lock up a large liquidity of a node, of a lightning node, for a long period of time. After that, you intentionally fail the uh, the payment. And just give me 1 second. And after you fail the payment, uh, you don't even pay a fee. All right. So in liquid in Lightning Network, if your payment doesn't go through, you don't pay a fee. So if I want to attack someone, I can route a very large payment through their node through a channel, right? So that all of their liquidity gets exhausted, and eventually I will architect that transaction in a manner that the transaction eventually fails. So I deprive the node of using that large payment that I have blocked for a long period of time, and after that I intentionally make sure that that payment fails and I don't even have to pay the fee for them, right? So they were not able to allocate those funds to any other transaction. I locked up that large fund, okay, and eventually I intentionally paid the payment. So I did not even pay them a fee for that. And same with slot jamming. I'll jam all their slots and eventually I will make sure that all of those HTLCs fail so that they were not able to process any more HTLCs and they don't even get any fee. All right. Do we have, what is the solution? Yeah, so we can have this. I hope like this is clear. Everybody understood what's jamming, what's liquidity jamming, and what is slot jamming. I think slot jamming or channel jamming. What's that? Yes, no, yeah, slot jamming. I hope everybody understood what's liquidity jamming and what's slot jamming. If you all did not understand what's liquidity jamming and slot jamming, please unmute yourself and let me know, or type if somebody's typing.
Yeah, I had one question of liquidity jamming. So if some node is trying to route a payment through another node of liquidity higher, of a large liquidity, then it will either go through, it will, or it will not, right? The point of Lightning payments being atomic. So how does it jam the route or the network?
Okay, so what I can do is that, okay, I have a node, all right, and I will create a payment such that my node is the initiator and my node is also the recipient, and there are 20 nodes in the middle. Okay, because my node initiates that payment and my node is the recipient of that payment, and there are 20 hops in the middle. So I have a channel with Alice, Alice has with Bob, Bob has with Charlie, Charlie has with Dan, Dan has with the fifth person with 6th, 7th, 8th, 9th, 10th, all the way to 20th, and then I'm the 21st person again. So I am sending a Lightning payment starting from my own node, ending at my own node, and there are 20 people in the middle. I'm routing that payment through those 20 people, eventually to reach my node only. When it reaches my node, I refuse to share the pre-image. Okay, I refuse to share the pre-image. Now there's a time lock. Within that time lock, I have to share that pre-image. Till that time lock expires, I will lock all of the liquidity, right? And when that time lock expires, then they will get a refund. So for that period of time, till the time lock expires, I will not share the pre-image intentionally, and all those 20 people, their liquidity have jammed, and I'm making a very large payment. I'm making a very large payment. I know that these people have a lot of liquidity, so I will create a transaction with a large payment. So all their large payments are locked till either the time lock expires or I share the pre-image, and I will not share the pre-image. I will make them lock their liquidity for a long period of time till the time lock expires, and after that they get a refund, and I don't even have to pay a fee. So they ended up locking their payment for no rhyme or reason for a long period of time, and they were not able to allocate those funds elsewhere and get fee.
Yep, makes sense. Thanks.
So what are some mitigations uh, to do away with this? One is HTLC. So there are three components that make up our proposed reputation scheme. So a node that is known to do that, a node that is a habitual offender that does this, that perpetrates jamming attacks or liquid jamming attacks, so called jamming attacks, right? One of the way of mitigating this is giving nodes reputation. How do you give nodes a reputation? One way could be HTLC endorsement, a binary signal sent with update at HTLC that indicates whether the forwarding node is willing to have its reputation held accountable for the behavior of a HTLC. Okay, so if Alice is giving a payment to Bob, Alice is the initiator, Alice sends a payment to Bob. Okay, and Bob has to route it further to Charlie. If Bob trusts Alice, Bob can tell Charlie that, hey, I trust Alice and I endorse Alice. Okay, I endorse Alice. So if you endorse people and they have a reputation of not violating contracts, then your reputation is also increased, because it means that you only communicate on the network with trustworthy people. So if Alice routes the payment via Bob to Charlie, Bob can endorse Alice's HTLC. Okay, Bob can say that, hey, I trust Alice. Okay, so this HTLC is an endorsed HTLC. If Alice has a reputation of not performing attacks, okay, then Bob's reputation also increases, because if you endorse for a person in a society or a network, and that person is an honest person, then that even uh, validates your judgment, right? You're good at judging people. So if when every time when I route a payment from Alice, I say that, hey, I know Alice, I trust Alice, it's an endorsed HTLC. Okay, so what happens is that if Alice is being truthful and those payments are going through, my reputation in the network also grows, because I am endorsing for the right people. So I'm a trustworthy person. The network will know that, hey, this guy Bob only endorses payments from trustworthy nodes, and if he's endorsing a payment, then he has a reputation, he has a history of endorsing that payment from trustworthy people. Okay, so you can use an HTLC endorsement scheme. Reputation algorithm. An algorithm used to determine whether a node's peers have good reputation based on its historical interactions. So you look at the historical interactions of a node's peers, and based on that, you give that peer a reputation. Resource bucketing. Division of a channel's resources into a protected bucket for endorsed HTLCs from good reputation pays, and a general bucket for all other traffic. Okay. So if like you can be connected to 100 people, 50 of them you endorse and 50 of them you might not endorse. So whenever you endorse, your endorsements will be in a protected bucket. Okay, so just because you have a good reputation, it doesn't mean that every single person that routes a payment to you is trustworthy. You might have a good reputation, but you might endorse 50 of your peers, you might not endorse 50 of your peers. So those peers that you endorse will be in a protected bucket, so people will get to know that, okay, this specific HTLC is coming from a peer that is being endorsed, that is in the protected bucket, so they can deal with that specifically. And if that is not protected, if you don't endorse that specific peer, that will go in the general bucket. So these are some mechanisms that can be used to classify nodes and give them a reputation score on the network, based on which we can reduce the jamming attacks. Okay, now one like I said, now this reputation mechanism has been there for quite some time. All right, so these developers were invited to jam a channel for hour and see whether this reputation allocation stands the test of time. So there was one attack known as the sync attack, which was able to violate it. Now, how did this happen? One attack was successful, a sync attack that aims to decrease the reputation of a targeted node's peers by creating shorter, cheaper paths in the network and sabotaging payments forwarded through its channels to decrease the reputation of all the nodes preceding in the route. To address the attack, Cohen and Schickelman introduced bidirectional reputation to the way HTLC endorsement is considered. When Bob receives a payment from Alice to be forwarded to Carol, Bob considers both whether Alice tends to forward HTLCs that are quickly settled and whether Carol tends to accept HTLCs that are quickly settled. Okay, so now what can happen is that up till now the mechanism that we had is that B was able to give a endorse the HTLCs of A. Okay, so B was able to endorse the HTLCs of A. But now B will also be able to endorse C. So we have bidirectional reputation now. Okay, because it might happen. See, even A is your peer and C is your peer, right? A is your peer and C is your peer. So it might happen that A is an honest peer. A always sends you HTLCs and settles them in time. But when you give it to C, C does not settle it well with D. C does not settle it well with D. So up till now, you have the unidirectional reputation mechanism where B was only able to give a reputation or endorse the HTLCs of A. Incoming HTLCs, you could only endorse HTLC endorsements. Now, the problem with that was that you can endorse A, but what if C misbehaves, right? C is also a peer. What if C does not give it to D? Then in that case, your peer will be having a bad reputation. You need to mark that as well, right? So now we have bidirectional reputation, okay, where you can not only give endorse the HTLCs of A, but you can also endorse the HTLCs of C. So this sync attack kind of bypassed this. Okay, the sync attack explored the possibility of a node B accepting an incoming HTLC from A and endorsing that HTLC and giving it to C. But then C further does not fulfill the contract, violates the terms of contracts with D. So B can now not only give a reputation to A, but can also give a reputation to C. So this mechanism that we saw of reputation, okay, where did it go? Yeah, this mechanism, this was only for incoming HTLCs. Now we have it for both incoming HTLCs as well as outgoing HTLCs as depicted over here. So the peer will be allowed to endorse the HTLCs of the incoming node as well as the node to which it is forwarding the payment. You want to read this? Let's just read this quickly in a couple of minutes. If Bob thinks both Alice and Carol are reliable, he'll forward and endorse the HTLC from Alice to Carol. If Bob thinks only Alice is reliable, he won't forward and endorse HTC from Alice. He'll immediately reject it. So if Bob thinks Carol is not reliable, he'll reject the HTLC. He'll not forward the HTLC to Carol, allowing the failure to propagate back to the original spender who can quickly resend using a different route. If Bob thinks only Carol is reliable, he'll accept and endorse HTLC from Alice when he has extra capacity, but he won't endorse it. Okay, so if Bob thinks only Carol is reliable and Alice is not reliable, if Bob has liquidity and if he has slots available, he will accept an incoming payment from A, but he will not endorse it to Carol. He will not say to Carol that, hey, it's coming from a node that I'm endorsing it to you. You accept it at your own risk. All right. So this is what a jamming attack is. We discussed what a jamming attack is. We discussed two types of jamming attacks: slot jamming and liquidity jamming. We saw what they are. We saw what are mitigations to fix it. One of them is reputation via HTLC endorsements. And we saw how up till now only incoming HTLCs were being endorsed. But now we have a proposal of bidirectional reputation where a node can endorse an incoming HTLC as well as an outgoing or an HTLC that it is forwarding. Any questions about this in a couple of minutes? If none, then we can move over to the question and answer session and take at least 2-3 questions in the next 10 minutes quickly. Anything in the chat section? Nothing. Cool. All right, so let's go through the question and answer session. What specific verifications are done on a fresh Bitcoin transaction and in what order? So when your node sees a new Bitcoin transaction, what checks does it perform to ensure that the transaction is valid? All right, so these are the checks that it performs. The transaction has at least one input and one output. Checks whether the transaction has one input and one output. And I think the Coinbase transaction is immune to this because you don't have inputs in a Coinbase transaction. So this excludes the Coinbase transaction. Other than the Coinbase transaction, it checks whether the transaction has at least one input and one output. the transaction is not bigger than the block size, right? The block size currently is what? 400,000 weight units or 4 virtual megabytes. So if a transaction is bigger than a block in size, it obviously cannot fit in the block. Each output amount is at least a 0. Okay, so you can't have negative amounts. You cannot have negative amounts, meaning the input is less and the output is greater, then the transaction will fail. The output needs to be either positive or at least 0. The outputs are in sum less than 21 MB, right? Because we only have 21 MB bitcoins. We have only 21 million bitcoins, right? So if a transaction is spending more than 21 million bitcoins, then it is an invalid transaction because more than 21 million bitcoins don't even exist. There are no duplicate inputs, right? So the transaction should not conflict with any other transaction that shares its inputs. That out points referenced in inputs are not undefined, right? The out points are not undefined, meaning the previous transaction that it refers to, every transaction refers to a previous transaction from which it is pending. That previous transaction should not be undefined, meaning it should be a valid existing transaction. If it's a Coinbase, the Coinbase field is not too long. So there's a limit to the Coinbase field. It should not supersede that. Checking that the transaction is not a loose Coinbase transaction. Rejecting outputs with excessive amounts of null data, bare multisig or dust outputs that cause transaction to be non-standard. So the transaction should be standard. Rejecting transactions shorter than 65 bytes of non-witness data. Refusing immature time lock transactions, meaning transactions whose time lock is not yet expired. Skipping transactions that are already in the mempool with the same WTX ID or TX ID, right? Because conflicting transactions cannot exist in the mempool. Scanning for conflicting inputs and rejecting conflicts with non-replaceable transactions. Then checking that any Coinbase inputs are mature, right? So the Coinbase transactions cannot be spent till 100 blocks are mined. Checking that the input amounts are in range. Checking that the input amounts can pay for the new outputs created. Checking that the transaction fee is in range. That the inputs are standard. The inputs have standard witness if applicable, that the SIG-ops limit are met, so the number of signature operations, there's a limit to it, they are met, that the transaction meets the minimum fee rate, there's a minimum fee rate as per the client that you are using, all right? There's a policy for relaying that transaction that should pay a minimum fee of X amount per virtual byte, that any replacement attempts do not exceed the conflict limits, that any transaction do not exceed ancestor or descendant limits, which currently is 25, checks that the maximum fee rate is not exceeded, that a replacement would succeed, and finally, that the transaction passes policy script checks and consensus script checks. So these are the checks that are performed when your node sees a transaction to validate that transaction. These are the checks that your node performs. That was the first question, and that was the answer to it. What is the second question? Why is my Bitcoin directory larger than my pruning data limit setting? All right. So to summarize this question, is the question summarized? So basically, this person was trying to run a node, and he pruned the node, right? What node pruning is, after validating the blockchain, we can get rid of a certain portion of the blockchain and only store a limited amount of blockchain. If we are working with constrained device which do not have a lot of space, then we can get rid of the blockchain. So this person was trying to run a node and he pruned the blockchain. Okay, this is the command that you give. He pruned the blockchain up to 6 GB. Now, despite that, the node was occupying 14 GB. So he was puzzled that when I have pruned the block size to 6 GB, why is my node occupying 14 GB of space on my device? And he wondered if pruning is working. So his question is, pruning is not working anymore. The answer says pruning controls the block size, the blockchain data. Pruning controls the size of the blockchain data itself is kept at by deleting old blocks after validation. Bitcoin Core, however, uses many other files to operate. Most of these are small, but some can have significant size, right? So the first is the chain state, UTXO set database, which tends to be 10 plus GB for mainnet these days. So even though you've pruned the blockchain, you still have to keep the answers on. Can everyone please mute themselves? Jami, can you please mute yourself? All right. Yeah. So even if you prune the chain, you still need to have the UTXO set with, okay, which today is around 10 GB in size. Blockchain indexes like the transaction index, compact block filter index, statistic, the mempool backup on disk, which is approximately 100 MB, wallet files, which may be big if they contain many addresses and or many transactions. Various other files that typically don't exceed a few MB in size. So it's not that you only have to store the blockchain, you also have to store a lot of other relevant information in order to validate transactions, in order to relay transactions, in order to validate blocks, in order to send payments, right? You need to store your wallet database, you need to index blocks, you have to keep a backup of your mempool, you have to keep the chain state. So all of these things also take up a lot of space. So that is the answer, that despite the fact that the blockchain was prone to 6 GB, all of this information also requires a disk space, and put together it was amounting to 14 GB. So if any of you are pruning your node, if you prune it to 5 GB or 6 GB, it does not mean that only 5 or 6 GB of space will be used or utilized on your device. There are a lot of other information, there's a lot of other data that also needs to be stored on your device. So that is the answer to this question. Let's try and take one or two more quickly, the easier ones. Let's take this one and the second last one. Yami, if you can hear us, can you please mute yourself? All right. How do I need to have set up to have get block template? So get block template is, it's basically an RPC command in Bitcoin Core. As the name suggests, what does it do? It gets a block template. Okay. Now this can be used in a testnet. Okay, but you cannot use it in mainnet, right? In mainnet, Bitcoin Core does not create a template in itself. It relies on an external software. So the questioner says, I tried using the command without arguments and it just returned an error. Do I need to have some kind of mining software set up? Does that software not already come with Bitcoin Core? How do I go about getting the software working either way? If you're not hearing anything.
Is there no way to another
I don't know. Can I? How you know how to do that?
Okay, he's muted now. Server muted. Somebody did that, I guess.
Right. I don't know who did. Anyhow. Good. All right. Yeah. Okay. Okay. All right. So yeah. So basically, this user was trying to issue this command, I feel, on the main net, and he was wondering why it's giving an error. So firstly, along with this RPC command, you also need to supply an argument with it, right? So if you submit get transaction, you have to also share the transaction ID. If you are submitting get block template, you also have to submit a JSON data which specifies the rules for that block. Okay, so an example would be that if you want to create a block template, a SegWit block template, then you give it this arguments: rules SegWit. Okay, so it will create a SegWit block template for you. However, the answer says the purpose of get block template is to return a list of the most profitable mempool transactions and some other data collectively called a block template. This some other data is the metadata, I believe, that you have in the header. Needed to try and solve the proof of work for the next block. This command is used by other software that doesn't come with Bitcoin Core that connects to your mining hardware and sends it instructions based on the block templates. So on the testnet, Bitcoin Core allows you to create block templates, but if you are on the mainnet, Bitcoin Core does not allow you to create block templates. Rather, your ASIC, your mining device, has a firmware that has the potential. So the firmware of your ASIC will issue this get block template to Bitcoin Core, and then it will retrieve. Bitcoin Core will then give the template to your ASIC software, and then your ASIC software or the firmware will then use that template to create a block which it will start mining. All right. So if any of you are running a node on the mainnet and if you issue this command, it will not work for two reasons. Firstly, because it also accepts an argument. Even if you give an argument, it will not work because Bitcoin Core in and of itself does not have the potential to create block templates for the mainnet. Your ASIC firmware has to interact with Bitcoin Core. Okay, you connect your ASIC with your node. Your ASIC firmware interacts with the node and asks your node to create a block template, and then your ASIC hardware device starts hashing or mining that block template. Let's take one last question in 2 minutes, and then we're done. Let's take this one because this is very new. So we have the concept of package RBF, which we've talked about in detail in the preceding Optech newsletter. Okay. Now, what this does is that it allows you to replace a package of transactions in the mempool with another package of transaction, right? So let's assume there's a transaction in the mempool, okay, and there's also a child of that transaction in the mempool, okay. Now that same transaction, parent transaction, which is in the mempool, has another child attached to it, okay, and this latter package pays a higher fee. So the latter package will replace the earlier package. Up till now, we have the concept of one transaction replacing the other transaction, which paid a higher fee, right? Which was RBF, which was one single transaction replacing the other transaction. But now we have package RBF. Okay, so a parent and child, a combination or a package of parent and child, which is in the mempool, can be replaced by another parent and child, conflicting parent and child in the mempool. Now there are two RPC commands related to it. Okay, the first is test mempool accept. So you check whether that package of child and parent is will be accepted by the mempool or no. Okay, so there's already a package in the mempool. You are trying to replace that package with another conflicting package. So you can use this command, but this command will give you a false error. It will say that it will give you a false reject. It will say that the package is not replaceable. But when you submit that package, it will accept. So prima facie, this looks like a discrepancy, right? I have a package, and when I ask Bitcoin Core whether this package will be accepted in the mempool, Bitcoin Core says false. No, it will not be accepted. But when I submit that package, it gets accepted, and it replaces the package that was already in the mempool. Now the catch here is that this specific command test mempool as accept does not match packages with each other. It only matches parent transactions. Okay, so it will only take the parent transaction of the package that is in the mempool and the parent transaction of the package that is conflicting and is trying to enter the mempool. And the one in the mempool is paying a higher fee, the one outside the mempool is paying lower fee. So it will say false. It'll say we can't replace. Okay, so test mempool accept will not take the entire package into consideration. It will only take into consideration the parent transactions that are conflicting with each other. But submit package will take the entire package into consideration. And that is why if the entire package is paying a higher fee, then the package will replace the package that is already in the mempool. Okay, so you should not get amazed when you want to replace a package in the mempool with another package. You test whether that is acceptable. It says no. You submit, it accepts it. Because when testing whether it's acceptable or no, it does not test one package against the other. It just tests the parent transactions against each other. But while submitting, it tests the packages with each other. So you might get conflicting answers. That is the final question of the week. We will not be able to cover the other questions, and core and Optech changes. Whoever is interested, there are just three all are related to about LND, one about Declare. You can go through it on your own. If you have any questions, you can post on a Discord, and relevant people will try to answer. And we are done for the session. I will stop sharing my screen. If anybody has any questions, then please feel free to ask your questions. Somebody typed something in the chat. Got to go, no worries. Yeah, if anybody has any questions, anything to share about the newsletter, about anything else, then let me know. And those who don't have anything to share, then the session's over. Please feel free to leave.